everybody, I am making this video to continue in lesson 8. I believe we did example 1. I know we did example 1 in class yesterday. Let's start with example 2. I'm going to jot down here what the product rule states. The product rule states that d dx, the derivative of the product of two functions, f times g, is f prime g plus g prime f. I'm not writing all those parentheses with the x's, like f prime of x times g of x plus g prime of x. That's just not really necessary for what we're doing right now. So let's start off and identify what f and g are. F and g are the two functions that are being multiplied together. F, it doesn't matter which one you take is which one, but I'm going to take f as the 6th root of x to the 5th. I don't like this pen. I'm going to take f as the 6th root of x to the 5th, which it's going to be helpful if we go ahead and rewrite that as x to the 5 over 6, because we will have to use the power rule to take the derivative of that. And I'm going to take g as 1 over x, which I will rewrite as x to the negative 1. Technically, you could just multiply these two together and find the derivative, but we are practicing using the power rule. F prime, the derivative of f, I'm going to bring my exponent of 5/6 down, and I'm going to decrease the exponent by 1. 5/6 minus 1 is negative 1/6, because that's 5/6 minus 6/6. I'm going to go ahead and find the derivative of g prime. I'm going to bring the exponent of negative 1 down in front, and I'm going to decrease the exponent by 1 to give me a new exponent of negative 2. And now we're going to take all 4 of these and plug them into our product rule. So we have f prime first, which is 5/6 x to the negative 1/6, multiplied by g, which is x to the negative 1, or 1 over x, doesn't matter how you write it. And then we add g prime, which is negative x to the negative 2. You can stick that 1 in front of the x or not. And that's multiplied by f, which is x to the 5/6. And now we're going to simplify this. So we have 5/6. These two right here, we combine those by adding. We have rules of exponents that tells us x to the a times x to the b is x to the a plus b. So negative 1/6 added to a negative 1 gives us a new exponent of negative 7/6 on x. Then I'm going to simplify the next two terms. Notice that we're just going to have minus now because we have the plus and the negative, so that's going to come together and just give us subtraction. Again, we are going to be adding these exponents. Negative 2 plus 5 over 6. That negative 2 is a negative 12 over 6. So negative 12 over 6 plus 5 over 6 is a negative 7 over 6. So we have x to the negative 7 over 6. But these are common like terms, because this is a 1 right here, and they both have the x to the negative 7 over 6, and so I can combine them. 5/6 minus 1 is going to give us a negative 1/6. So I got the negative 1/6 by doing 5/6 minus 1, because the x to the negative 7/6 makes them like terms. So our final answer is negative 1 over 6 times x to the positive 7/6. Or you could rewrite that as negative 1 over 6 times the 6th root of x to the 7th. Third example, example 3, we're going to look at that also again using the product rule, but this one's going to be a little bit more involved, because f, I'm going to say, is x to the 3rd times sine x. And g, I'm going to say, is cosine x. Let's find g prime first. The derivative of cosine is negative sine. So that's pretty much done. But to find f prime, f is a product of two separate things. F is a product of x to the 3rd and sine x. So to find f prime, we have to use the product rule again. So we're using the product rule while we're using the product rule. So down here, I'm going to start a smaller product rule where f is x to the third and g is sine x. The derivative of f is 3x squared, and the derivative of g, derivative of sine, is cosine. So now to write f prime, I'm looking at f prime g times, this g should have a prime on it, times g prime f with these four. So f prime g is 3x squared times sine x. That's me multiplying f prime and g. Then I'm going to multiply g prime and f, the cosine and the x to the third, plus x to the third cosine x. And remember, we got that from filling out f prime g plus g prime f. Okay, so far we had to use the product rule to find f prime that we were already looking for inside of using the product rule. So it is these four pieces, this f, this g, this f prime, and this g prime, that we are going to use to fill out f prime g plus g prime f to give us the derivative of our original function. So now let's start filling this out. F prime, that's 3x squared sine x plus x to the third cosine x. That's multiplied by g, which is cosine x. And that's added to g prime, which is negative sine x. And that's multiplied by f, which is x to the third sine x. And then I'm just going to clean this up a little bit. I'm going to distribute this cosine to both of these terms in the front here. So we have 3x squared sine x cosine x plus x to the third cosine squared x. And then I'm just going to multiply this negative sign with that sign. Notice that we'll now be working with just subtraction here. So we have minus x to the third sine squared x. And there's our final answer. Now we had already looked at example 4 in class together, so let's look at example 5. This time we are now using the quotient rule. I need to still start off by identifying f and g. F is whatever is in your numerator. So our f is 3t squared minus t to the 1/2. I did not write the square root of t. I just went ahead and rewrote that as t to the 1/2. G is what's in your denominator, so our g is 5t. We need to take f prime. I'm going to take the derivative of f using the power rule. So I'm going to bring my exponent of 2 down, multiply it with the 3 that's in front to give me a 6, and my new exponent on t is 1. Then I'm going to bring my 1/2 down, and the new exponent on t is 1/2 minus 1, which is negative 1/2. For the derivative of g, the derivative of 5t is simply 5, because the derivative of t is just 1. I wanted to put this in a different color. Now, to write our derivative, we will be using the quotient rule. These are the 4 things we need. What the quotient rule tells us is that g prime of t, which is what we're looking for. By the way, y'all, this g of t is not at all to be confused with this g. Right? These f and g's here are showing up from the quotient rule. It doesn't matter that the function was named f or that the function was named g. I hope that's clear. We can talk about it in class if it's not. G prime of t, the quotient rule says this is equal to f prime g minus g prime f all over g squared. So I'm going to start filling these things in. F prime is 6t. And by the way, y'all, before we put f prime in there, let's do some simplifying here. I'm going to rewrite f prime as 6t minus 1 over 2. I'm going to put that t to the 1/2 in the bottom because it had a negative exponent. And remember that the 1/2 exponent is the same thing as the square root. So I'm just going to go ahead and rewrite f as 6t minus, f prime as 6t minus 1 over 2 root t, which is what I'm going to put right here for my f prime in my product rule, in my quotient rule formula. So we have f prime, and that's multiplied by g, which is 5t for us. Quotient rule says to subtract in the numerator, and we need g prime, which is 5, and that's multiplied by f, which is 3t squared minus the square root of t, or t to the 1/2. Same thing. So what I'm saying is that this is the same as 3t squared minus the square root of t. Only reason I rewrote it with the 1/2 power was so that we would be able to see the exponent when we had to go do the power rule. This is all divided by g squared. If g is 5t, then g squared, you have to square 5t. Square the 5 to get 25 and square the t to get t squared. So this is all over 25 t squared. And this is our answer. I'm just going to clean this up a little bit. I'm going to distribute some things and see if we have any things that we can collect. So I'm distributing this 5t here, so I'm going to get 30t squared. Also distribute the 5t to the negative 1 over 2 root t to give us a negative 5t over 2 root t. I'm going to distribute this 5 to that 3t squared to give me a negative 15t squared. And I'm going to distribute this 5 to this negative root t to give me a positive 5 root t. Because remember, this right here was already negative, and that's negative. So that would give you a plus sign down there. And then in the denominator, we still just have 25t squared. There are some like terms in the numerator that we can combine. We have a 30t squared and a negative 15t squared. That's going to leave us with a 15t squared. Let's talk about what else we can simplify in the numerator. Right here, 5t over 2 root t. That is 5t over 2 t to the 1/2. That's the same thing as that. Subtract those exponents. So we still have the 5 over 2. The new exponent on t is 1/2 because I did 1 minus 1/2 to leave me with 1/2. So we have 5. I don't know why I wrote that, y'all. So we have 5 over 2 multiplied by the square root of t. That square root of t is in the numerator because 1 minus 1/2 came out positive. So I'm just going to rewrite that in the second term here. Remember, that was all coming from that term there. So this is 5 over 2 root t. And then I'll bring down my plus 5 root t. Remember, the two purple terms combined to give me that one. But now, the whole reason we did that is because now these are like terms. The negative 5 over 2 root t and the positive 5 root t. So I'm going to combine those into a single term. Negative 5 over 2 plus 5 is a positive 5 over 2. And the last thing you could do to simplify this is you could take a factor of 5 out of everything because all three of these numbers are divisible by 5 to leave us with 3t squared plus 1 over 2 root t all divided by 5t squared. This is not the only way that the final answer could be written, but I would leave it like that. You may wonder, that's a squared. You may wonder, why do we have to go through all of this algebra? Because technically, we had this answer from back here. It just wasn't very simplified. Remember what we're doing, y'all. We're finding the derivative. The derivative is important. The derivative gives us a lot of information about when the function is increasing, when the function is decreasing, when the function has a max or a min. And we'll see examples of all of that as we go through the rest of the calculus course. But the point is, we will be using our derivatives to do more things with the functions. And in order to use the derivatives, we will need to have the derivative in a simplified form. Because once we find the derivative, we will start setting it equal to 0 and solving equations. We'll start factoring things. And so we need to be able to not just find the derivative, but also to use algebra to simplify it down to something that we can work with. And so that is why we are doing this. Ignore that. In class yesterday, I talked about number 6 briefly about how we knew the answer was going to be y minus y1 is equal to m times x minus x1. I said that x1 was -1 and that we would need to plug that in. I said that we could easily find y1 by plugging -1 into the function. And we talked about how we would find m by plugging -1 into the derivative. So the first thing you're going to have to do is you're going to have to find h prime, find the derivative of this function. By the way, you will have to use the quotient rule because that is a quotient. And then once you find h prime, then you will plug -1 in to get your slope. And then you can fill out the equation of your line. I'm going to leave this problem as extra credit. But to help you get started, this is not much help, but I will rewrite h of x as 1 minus x to the -2 over 3 minus x squared. Admittedly, maybe it is help because I think that number 5 with that square root and some of these fractional exponents is a little bit more involved than number 6 is going to be. So, I have not done any derivatives here, right? I haven't done any derivatives. So you still need to go and find f, g, f prime, and g prime and fill out the quotient rule to find your slope. The good news is, though, you all, especially if you're going to attempt this for extra credit, and I think you should, once you get to this point, once you've found all 4 of these things and you have plugged them in to the quotient rule, so that's essentially the same point we were at right here, right? You do not have to simplify it. You do not have to do a whole bunch of simplifying because all you really need to do is plug -1 in. So what I'm saying is that basically if number 5 were number 6, I would just plug -1 into all of that. And then I would have my slope because I didn't need the general derivative. I just need to know what the derivative is at -1. I hope that's making sense. But try that for extra credit. We can talk about it during class if there's any questions about it. Here we are given at the top of this page the derivatives of all 6 of our trig functions. We already had the rule for cosine and we had the rule for sine. We also already had the rule for tangent because we did establish it when we used the quotient rule to find the derivative of tangent. But now we have all 6 of our rules, and so now we're going to find some more derivatives. Example 7, we want to find the derivative of sine x minus cosine x. You think of this as the derivative of sine x. And again, you all, this step is really optional, writing this like this. If you haven't already, you will get to the point where you're comfortable enough to automatically just say, oh, the derivative of sine is cosine, and the derivative of cosecant is negative cosecant cotangent. That's a new rule, so maybe you're not comfortable saying that yet. But my point just being that you don't have to write this derivative notation. Okay. Let's be careful with our signs here, you all. There was already a minus sign in the problem, and then the derivative of cosecant came out negative. All C derivatives are negative. So this will turn into a plus sign down here because we have those 2 minuses. As our final answer for f prime of x. This should say f prime, y'all. F prime of x. Example 8. I'll go ahead and break this up into some separate derivatives. I'm going to do a few steps in one. I've gone ahead and pulled out my constant of 5, and I'm also pulling out this constant of pi over 2 in front of cosine x. And now I'm going to go up and look at some derivative rules. The derivative of tangent is secant squared. So we keep the 5 in the front and we multiply that 5 by secant squared x. I'm going to bring down that minus pi over 2. And the derivative of cosine, I didn't mean to say in purple, but the derivative of cosine, we knew that rule from a couple lessons ago, is sine. So just this derivative of cosine here is negative sine, excuse me. All C derivatives are negative. The derivative of cosine is negative sine. So we have 5 secant squared x, again plus, because we have these 2 minuses, pi over 2 sine x. Number 9, we have x to the 5th times secant x. We have x to the 5th times secant x. We have a product of 2 functions, so we will have to use the product rule to find this derivative. F is going to be x to the 5th. g is going to be secant x. The derivative of f is 5x to the fourth using the power rule. The derivative of g, the derivative of secant, look at the top of the page, the derivative of secant is secant tangent. So g prime is secant x tan x. Now that we have all four of these, we can fill out h prime, which is what we're looking for, using the product rule. F prime g plus g prime f. So f prime is 5x to the fourth. G is secant x. G prime is secant x tan x. And f is x to the fifth. I'm going to write the x to the fifth in the front because I think it looks weird to stick it back there, because then that might look like tangent of x times x to the fifth. And we don't really need that parentheses on the 5x to the fourth. So I'm just going to write it one more time without those parentheses to get our final answer for h prime of x. The last thing we will talk about in lesson 8 is higher order derivatives. Higher order derivatives is taking the derivative multiple times in succession. So we have the first derivative. We've done a lot of problems where we have found the first derivative of things. And then if you take the derivative of the first derivative, you get the second derivative. We did that for the first time yesterday when we found an acceleration function, because acceleration is the second derivative of position. So first you find velocity with the first derivative, and then we found acceleration with the second derivative. You could keep going and find the third, fourth, fifth, so on and so forth. Just a notational thing here. First derivatives, we just get 1 prime dy dx. Second derivatives get 2 primes. It is d squared y dx squared. Same notation for the third derivative. Once we get to the fourth derivative, we no longer write 4 little 1, 2, 3, 4, because after a while that's going to get annoying to count. We just put the 4 in parentheses as an exponent. And it's not an exponent, but that's just the way that we write it if we're talking about like the 7th derivative or the 8th derivative. So that's the 10th derivative of y. Find the indicated derivative. For h of x, let's find h double prime. And then down here for p of x, let's find p to the third, or p3, the third derivative. So first, to find h double prime, we have to first find h prime of x. And to find the derivative of cosecant, we use the derivative rules that we had up here. The derivative of cosecant is negative cosecant cotangent. So h prime of x is negative cosecant x cotangent x. That is just the first derivative. To find the second derivative, we will have to use the product rule to take the derivative of this again, because we have these two functions multiplied together. So I'm going to say that f is negative cosecant x, and I'll say that g is cotangent x. And then we're going to need f prime, and we're also going to need g prime. F prime, the derivative of cosecant x, or the negative derivative of cosecant x. I'm looking at this same rule here. The derivative of cosecant is negative cosecant cotangent. The derivative of cosecant is negative cosecant cotangent. There was already a negative there. And the derivative is negative cosecant cotangent. So that's going to come out to be a positive cosecant cotangent. The derivative of cotangent, going back up to our rules, is negative cosecant squared. The derivative of cotangent is negative cosecant squared. So for g prime, there we go. We are filling in negative cosecant squared. Now we have all 4 pieces that we need to fill out h double prime of x, because we already had the first derivative. We're using the product rule, f prime g plus g prime f. F prime is cosecant x cotangent x. G is cotangent x. So this is multiplied by cotangent x. Make sure we see where everything's coming from. G is cotangent x. F prime was cosecant x cotangent x. And then to that we are adding g prime, which is negative cosecant squared x. I'll just stick that in parentheses there. Multiplied by f, which is a negative cosecant x. So Now let's do some simplifying in here. In the first term, we have two cotangents being multiplied together. And so we're going to have cosecant x, cotangent squared x. Cotangent squared is coming from those two cotangents coming together. Careful with your signs here. We have a minus minus. This will stay as a plus. And we're multiplying a cosecant squared with a cosecant. So we're getting a cosecant cubed x. For our last example, we want to find the third derivative here. If this were a problem like on a test or a quiz or something like that, I would not expect you to use the product rule to find this derivative. For example, up here, this function, you definitely have to use the product rule to find that derivative. I guess you could use the quotient rule if you like start rewriting it to get some trig identities, but that's not necessary. I think the product rule is more straightforward there. But for number 11, you do not have to use the product rule because you can first just simplify the original function by distributing the 3x squared to get 3x squared minus 15x to the third. And then you can start taking the derivative using the power rule. So p prime of x, just the first derivative, bring the exponent of 2 down, multiply it with 3 to get 6. And the new exponent on x is now 1. Bring the exponent of 3 down, multiply it with the 15 to get 45. The new exponent on x is 2. That's your first derivative. For your second derivative, the derivative of x is 1, so the derivative of 6x is just 6. Bring the exponent of 2 down, multiply it with the 45 to get 90. The new exponent on x is 1. Then for your third derivative, the derivative of 6 is 0, and the derivative of negative 90x is negative 90. So we get our answer that the derivative is negative 90. The third derivative is negative 90. Keep in mind that does mean that the fourth derivative would be 0, and all other derivatives would be 0 after that. Because the derivative of any constant is always 0.